Good time of the day, everyone, and welcome to the EPIC online technology meeting for materials for photonic chips. This is a series of online events we do on different aspects of photonics, and today we have a very exciting topic on these materials. Let me remind you that EPIC is the largest photonic industry consortium in the world that comprises over 800 corporate members, and EPIC is there to serve you with technology expertise, market knowledge and reports, opportunities in investment, in recruitment and marketing. So we have a very exciting agenda today that covers several interesting materials that come now on the stage in the field of integrated photonics. And we'll hear from 7 speakers today representing La Luce Cristallina, the Seacraft, Alluvia, SAES, SIA Systems, Buchler Group, and Epiphany. I'm very excited to be moderating this event today, and I'm also very excited to see the large audience we have today. We have representatives of all the levels of supply chain in this field. You can see that we have a lot of people working in R&D and also in the actually supply of those kind of materials, as well as component manufacturers, equipment manufacturers, metrology and testing, contract manufacturers, and software and design, and of course several end users and integrators represented today with us in the room. So I hope this will be a very interactive meeting. We aim here to build partnerships and relationships across the supply chain in this topic. And yeah, I'm looking forward to our presentations with no excuse. I also would like to give you some heads up about the upcoming offline events of EPIC. The next one we will have will take place in Munich alongside with the Semicon Europe Expo at Messe Munich. And together with that, the day before, we will have this event dedicated to bridging the microelectronics community and photonics community. We'll have 2 very exciting sessions that bridge the integrated photonics with 3D integration and also integrated photonics with wafer metrology technologies. And we'll have a very nice lineup of speakers, including XFAB, Basic Group, ASML, and ZEISS. So please mark the date of 17th of November, and I hope to see you there in Munich with us. And now, yeah, without further delay, I'd love to introduce the first speaker of today's session that will bring us to the realm of materials, innovative materials that come on the stage in integrated photonics. So our first speaker is Alexander Demkov. He's a co-founder and a CEO of La Luce Cristallina in Texas, as well as a professor of the University of Texas. Welcome, Alexander. Maybe you need to unmute yourself.
Yes, Ivan, thank you very much for kind words, and thank you for the invitation. This is very exciting.
You're very welcome. Whenever you're ready, you can put up your presentation, and we're all ears.
All right, so now first let me share.
So Alexander will talk about ferroelectric materials for electro-optic modulators, and particularly about the famous BTO material.
It says that something else is sharing, which is probably you.
Try now.
Okay, so I share this. Did it share? And if I then share the presentation, can you see it?
Yeah, so good. Flow is yours.
Excellent. Thank you so much. And thank you very much for the invitation to present at this meeting. It is very exciting for us. As Ivan said, I'm the co-founder and CEO of La Luce Cristallina. And we are a very small startup in Austin, Texas, and we make materials, barium titanate on silicon, for electro-optical modulators. Let me choose the pointer. Okay. So what about the modulator? So modulator is the active component in the photonic integrated chip, and essentially most interesting one can modulate either the amplitude, sort of the intensity of light, or they could be phase modulators. Phase modulators also can change the intensity of light through various effects. They also can have multi-level systems. In practical implementation, as shown here on the right, essentially they're waveguide modulators, some resonance structures, or interference devices. So this, for example, is just a phase shifter. This will be a ring resonator, and this is a Mach Zehnder interferometer. And so they all have pluses and minuses, and depending how you want to make them, they will use different physical effects. So for example, in phase change materials, if you want to have an amplitude modulator, you can do a phase transition, and in one phase material lets light through, in the other one it doesn't. Let's say it's a metal to insulator transition. You also can use carrier modulation by various effects, and essentially you're changing your refractive index of material by changing the number of carriers available. And these effects are right here. I am mostly interested in these two on the left, and specifically in the Pockels effect. And these are kind of boring, very classical effects where you apply electric field and it allows you to change refractive index either linearly in the strength of the field or quadratically. So one is Pockels, another is a Kerr effect. Just to put this all in perspective, why we're doing all this, why we have companies which make wafers for photonics, it's because the silicon photonics came into very interesting time frame, right? So on the left here, you can see the number of components. Now, components are not necessarily modulators. They're all kinds of components, delay lines, splitters, combiners, and so on. And there are two sets of materials. Essentially, it's silicon, monolithic silicon, and it's 3,5s like indium phosphate or indium phosphate and gallium arsenide on silicon integrated heterogeneously. And the important thing here is that if you look at this time frame, 2025, the silicon is in the realm of 10,000 devices on a peak. And so this is very large scale of integration. And so in some sense, photonics repeats the process which we observed over 70 years in silicon electronics, where you go from single component devices to integrated circuits, then very large integrated and ultra large and so on. But the important thing is that we're now in silicon at the VLSI level. And why is it important? It's because here below is the data I lift from a Dutch foundry, and it essentially tells you what kind of wafer you want to use to be economically viable. And so here they pick up some average peak with it's a small one, probably a channel with 10 square millimeters. And the idea is that if you produce 10 million of these peaks per year, so it's right here, then it makes sense to go from the green line to the black line because it will be economically more viable. And black line represents 200 millimeter wafer. And now it's hard to estimate how many PICs are being sold per year, but we got a glimpse of that when Intel sold the portion of photonic division to Jabil. And so I think we are right about here on the cusp where you go from green line to the black line. And so that's, for example, why Lelucci focuses on 200 millimeter wafers. Now, in general, here is a recent review by Sorif and Company telling you what kind of different materials you can use for modulators. So at the top here, this is typical silicon. Then you go to germanium and silicon alloys, 3,5s, polymers and other materials working on Pockels effects, phase change materials. And here they are kind of rated from the point of view of how they are compatible with silicon manufacturing. For example, if you use silicon with thermo-optic effect, it's real easy to bring it into CMOS foundry because it's straight silicon. The highlight of this technology is extremely low loss. The limitations are power consumption across talk because silicon has high thermal conductivity and you need to run current to warm it up to change the refractive index. And so if you look at the materials which are ferroelectric, which will be lithium niobate, barium titanate, and ferroelectric polymers, they are right here. And you can see that, for example, there are issues with their integration in the flow of the CMOS foundry. But they do have other good qualities. For example, lithium niobate has an exceptional bandwidth. And then they do have some drawbacks. For example, barium titanate, just not much is known about it, so nobody wants to bet on a new technology. Polymers cannot take very high temperature. I think ATC is as far as they can be pushed. So, for example, for defense applications, they're not ideal. And you need to seal them because they don't like the environment. Lithium niobate is a great material, but the devices are large. And so I think that all of them will play a role in specific markets. And so now just let's look at the market. This is, thank you, Epic. We've got access to your old data. So this is sort of the data for last year. So here is normal silicon, and this is lithium niobate. And so you can see lithium niobate is relatively small. One comment I would like to make, because my background is in CMOS, the whole market is relatively small. The excitement is because people project cumulative annual growth rate of 43%, which implies that by 2029, which is not that far away, it's like 4 years down the road, for example, lithium niobate in various forms will be essentially a billion. So they have a growth rate of 98%, which is gigantic. Everybody else is sort of here, so they're more of a niche material. So, they even put barium titanate. And so the question is, why, what drives, this is a very rapid expansion from 32 million to a billion, essentially. What drives that? So let's look at the challenges of plain silicon photonic modulators. So they're not very new. So this is Richard Soref, who is commonly accepted as the father of silicon photonics when he worked for Air Force Research Lab in Rome, New York. They published a paper in 85, I believe. This one is from 87. And they suggested the waveguide modulator in silicon. And in very short period of time, they become from like exotic thing to a mainstream. They do suffer from slow switching speed. They're fairly large, but the devices have very low insertion loss. So there will be various loss data here, and it's different. So for more advanced technologies, this is like overall insertion loss. What happens if you have a waveguide and you put the device in? For more sort of out there materials, they talk about the waveguide loss, which is, of course, just a straight waveguide. The main, I guess, selling point for silicon photonics in that form is its excellent manufacturability. It's essentially a silicon process, and the devices are fairly large, right? So waveguide is a micron scale. So the processing itself, by sort of CMOS standards, is fairly straightforward. And then there are like two kinds of silicon modulators. There are those which work on thermo-optic effects. So you have a heater above them and you heat them locally. And then you can have those which work on like Franz Geldish effect or plasma effect. You're moving the charges back and forth. Now, the new demands, particularly after COVID, on the network traffic, data centers, and now AI, put some pressure on silicon fabrication, right? You need to have very high modulation efficiency, VPI below 3.5 volts. They have to be fairly small, need to have a low insertion loss, large bandwidth, and most importantly, very small power consumption. This is on the order of picojoules per bit. And so this is a real challenge for silicon. And so people look at other things which they can use to modulate. So one thing comes to mind is indium phosphate. The material has astonishingly low propagation loss, very high modulation efficiency. VPI is volt and a half. They're very small. Note that the silicon devices are close to centimeter in length. This is 100 microns, so it's very small. And they have very high bandwidth. The problem is manufacturability. Indium phosphate, there's nasty chemicals with phosphine, and also a small wafer size. So silicon is commercially 300 millimeters. A lot of it is 200 millimeters. Indium phosphate wafers are much smaller than that. Electro-optic polymers, they're the ones which are close to my interest. They work on Pockels effect, essentially, but they have very high insertion loss. They have limited manufacturability, and the temperature is an issue. And also you have to seal them somehow from the environment because they're not very strong. but they have very, very fast switching speeds on the picosecond scale, and they are fairly small, millimeters. So they satisfy some requirements and do not satisfy others. Let's see, let's go down. Lithium niobate is a fantastic material, and it's no wonder that everybody is excited about it. It has a very low insertion loss. It's working essentially on the phonon frequency and terahertz frequency, and it's ultra fast switching speed. Now, the issues are the devices are fairly large, and we'll talk about why they're large. But to me, the biggest concern is manufacturing compatibility. It's not so much lithium niobate, it's lithium oxide. Lithium oxide is extremely volatile. At room temperature, it's giving you significant vapor pressure. And so if you bring this to silicon fab, you contaminate everything, and lithium is a known contaminant in silicon process. So it is a concern. You have to build the entire separate infrastructure. So here's some comparison in terms of, let's say, bandwidth, the size of the devices, and it's in this slide. Where is my slide? What happened to it? I don't know why it's here. It should be here, and it should be a laser pointer. Yeah, okay. So you can see that barium titan is actually pretty good. Lithium niobate is excellent, of course. And then this is the VPIL, right? So it's somewhat device dependent, but that's efficiency of modulation as a function of propagation loss. So on this one, you want to have VPIL as small as possible and propagation as small as possible. So you'd like to be in this empty corner. On this one, you want to have a high bandwidth and you want to have small length. So you want to be in the upper corner. And this is, so barium titanate, my main topic here would be actually pretty good in that regard. So among all kinds of modulators, I'll focus on those which do phase modulation, clean phase modulation. So they're essentially phase shifters in various forms, and they use Pockel's effect. And I will not talk about polymers, but I'll talk about lithium niobate and barium titanate. PZT is another option, but PZT has lead, and so this is a no-no. And so the reason these materials are popular is because of the high data rate they offer and low energy of switching. So they allow a low energy solution, which is attractive for data centers. So linear electro-optic effect. Essentially, the effect is right here. This is a refractive index. It's the ratio of the speed of light in vacuum to the speed of light in the material, so it should be lower. So it's always larger than 1 unless you do something tricky. And it's a function of electric field. So essentially, you are slowing light in the material. And here, this is Friedrich Pockels. He was a German physicist who came up with this effect. And this is a table I lifted from Stefan Abel's chapter in the book we published a few years back. These are Pockel's coefficients for a lot of good materials, and you can see that everything on the right here essentially is a ferroelectric. So here's lithium niobate. It has the Pockel's coefficient of 35. And here is barium titanate, which in the bulk form has a Pockel's coefficient of 1,300. Potassium tantalate is better, but it's potassium and tantalum, and so they're not very good for silicon manufacturing. So what happens when you take a ferroelectric and you put it under strong electric field, right? So you put positive charge on this side, negative charge, so here's the electric field. In terms of refractive coefficient, it's convenient to think about the change in the dielectric constant. So what I'm showing here, it's a formula. It's a derivative of the dielectric constant with respect to electric field. So when you place a material in the electric field, the first thing which happens, here's your band structure, and the chi1, the linear susceptibility, is calculated from the transitions from the valence band to the conduction band. So light comes in, you have these transitions, that gives you chi1. If you apply strong electric field, strong enough that you tilt the band structure in such a way that these transitions are all different, you will get different susceptibility, and that's described by chi2. It's a second order susceptibility. It's a change in susceptibility, essentially tells you that the dipole is not proportional to the field, it's proportional to the square of the field. So that's the main effect in a material like gallium nitride or indium phosphate. It's a very fast effect because it requires electrons. But because you have a ferroelectric, two other effects contribute to the overall change of the refractive index. So because it's a highly anharmonic material, what happens if you pull on the ion, like so. This is the potential energy which an ion feels. If you pull it away from the equilibrium and interrogate it, if the crystal is harmonic, the resonance frequency is the same no matter where you are on the potential energy surface. But if it's anharmonic, which all the ferroelectrics are, you can change the frequency. This is commonly described as a Raman effect. And so this here, the d chi1 d tau, is the derivative of the susceptibility with respect to atomic displacement. That's a Raman susceptibility. And that is a very strong factor in the change in the diffractive index. Another effect is this one, and that's the converse piezo effect. When you apply strong electric field, your ferroelectric, the old piezoelectric in the same time, it changes the size. If you change the size, the width of the bands changes, the band gap changes, and so all this transition change, and so chi1 would change. And the more field you apply, the more it changes, and that's described by this piezo component. So for the purpose of our discussion, remember there is red, green, and blue components to the Pockels effect, and they all respond in different mechanisms. So this is electrons, this is optical phonons, and this one is acoustic phonons or strain. And so they respond differently to different stimuli. So if you look at barium titanate and lithium niobate, barium titanate has a phase transition to a ferroelectric phase where it loses inversion symmetry, and that's where it gets the large Pockels effect. And we actually know what drives it. So here's, for example, the atomic displacement for various phonon modes, 15 modes of the unit cell, projected on every atom. And so the modes 4 and 5, which are actually driving the most or large portion of the Pockels effect, barium doesn't do anything. It's a movement of titanium and oxygen like here. And that's the contribution. This is around susceptibility. What it amounts to, if you look at how each effect of this red, green, and blue contributes to the Pockels response, electrons don't do much. So the largest one, R33 electronic, is 2 picometers per volt. But the largest optical phonon one is 800. That's R42. It's 816 picometers per volt. So it's very large. And you'd say, where's the 1,300 comes? Well, the other 600 comes from strain. And so that immediately tells you that barium titanate is versatile. At low frequency, optical phonons are depopulated, so you rely on strain, and you still get like 600 picometers per volt. If you go above the acoustic resonance, lattice cannot respond, but optical phonons would work up to terahertz. So it would roll off, but it'll still be fairly high. Now, if you look at lithium niobate, it's a different kind of material. It's an order-disorder transition. And so if you again look at the components, so the R33 is completely dominated by it's a clamped, or it's essentially ionic, it's optical phonon. A little bit of it comes from electrons and a little bit more from strain. So if you take lithium niobate, it would work very well up to high frequencies, but if you go to low temperatures, it will roll off very significantly. And that's sort of, so when you design a structure, you have to think of application. So barium titanate has much better prospects at low temperature than lithium niobate. How do you integrate that? So this is how we integrate, but I think most people do the same thing. You start with clean silicon. You put strontium titanate. It's a buffer. It's a perovskite buffer, reasonably well lattice matched to silicon. And then on top of that, you can grow barium titanate, this purple thing. You can grow by MB. You can grow by RF sputtering, which we do. You can grow by sol gel. It doesn't matter really how you grow. Once you've got strontium titanate buffer on silicon, you can grow high quality barium titanate. This is some crystal data, but I think you'd like to see what it looks like. So this is silicon. This is a silicon substrate. And this is the barium titanate on STO buffer. You don't see STO is too thin crystal. So it's a high quality crystal grown on silicon. And then there's a version of that where you actually don't have any silicon between barium titanate and the box of NSOI wafer. The carrier silicon wafer is below, is out of the field of view. So these are thin films. Now, if you look and compare the thin films of lithium niobate and barium titanate, let's take the A-axis variety. That's a long axis in the plane. So lithium niobate gives you a single domain structure, and the data came from your Lutfeld group at ETH. Barium titanate is more complicated. It has domains. It can grow in two orthogonal orientations. You see there dark green and light green. They are the same crystal structure, except the long axis, it's at 90 degrees. If you look at the dielectric tensor in lithium niobate, it's extremely stable at frequency, no change. In barium titanate, there is change, so it rolls off. If you look at the electro-optic coefficient, it's quite the same thing. In lithium niobate, it essentially does not change. It's a modest value. It's here. It's in thin film. It's below 30 for R33. In barium titanate, it's a thin film, so you don't get 1,300. You got something smaller, and then it rolls off. But actually, it's still large. It's still over 200 when you go to very high frequency. Let's see. Let's see what devices look like. So this is La Luce Cristalina doesn't make devices. We collaborate. So this was a collaboration with Professor Wasserman at UT Austin, and he built both ring resonators and Mach-Zehnder interferometers. So there's a picture of Mach-Zehnder, and here's a picture of the ring resonator. So they showed a fairly low loss in a waveguide. This is just a straight waveguide loss obtained by cutback measurement right here. So you make different waveguides of different length and plot that. And they were able to get the resonator with a Q of 10 to the 5th, which is not bad. And this was 2023. But there is rapid progress. And remember, he's working with graduate students, so they're not real engineers. And so in 2025, they used just resonators, racetrack, and this is ring resonator. And they were able to extract the linear loss in the straight part of the racetrack on the order of 0.14 decibel per centimeter. And this is really fantastic, and that's before polling. So none of this barium titanate is polled. Lithium niobate is always polled before, at the wafer level, before you bond it to a substrate. And so there is rapid progress. We're not the only people who work on that. So this is data from IBM, and they reported Q of 10 to the 5th and loss of 0.8 decibel. This is data from a company called Phase Sensitive. They did a very interesting experiment. They made a 3.5 centimeter long waveguide, and they sent light in and waited for light to come back. So effective travel length is 7 centimeters. So it's not millimeters, not microns, it's 7 centimeters. And they measured the loss of 0.7 dB. And then this is the work on the right from University of Illinois in Champaign-Urbana. They actually made the record Q of 1 million resonator, and they extracted the loss of 0.3. What is behind this? If you look at the old literature, for example, the old IBM papers, the loss is much, much higher, on the order of like 40 dB. So what's the difference? All of this data is in the monolithic barium titanate. So nobody put silicon or silicon nitride and etched that. Guiding is done in barium titanate proper. And also most of them are done in barium titanate grown on large wafers. So here's the data from the company DCA Instruments that manufactures the deposition tools. And this came from, I think, PsiQuantum. This is a paper they put on archive. And this is the uniformity data on a 300 millimeter wafer, right? So 300 millimeter. Remember that we're just barely touching where 200 millimeter is financially viable, but 300 is good because it's even bigger wafer. And you can see they show this is a 3 sigma deviation, excellent thickness uniformity across the wafer. Lattice parameter doesn't change. Rocking curve, that's the quality of the Fourier transform of the real space lattice, is very good. And so refractive indexes also doesn't change very much, and they claim the Pockels coefficient in the order of 1,000. So to finish that, let me leave you with a table which sort of compares properties of various materials by various metrics from, modulation mechanism, mostly Pockels coefficients that I'm interested in, refractive index, dielectric constant, modulation length, V pi L, reliability, and how difficult it is to integrate with silicon flow. And we have just started as a company manufacturing barium titanate on a 200 millimeter wafer. And so probably my time is up. I will stop here. Thank you very much for your attention, and I will be happy to answer all the questions.
All right. Thank you very much, Alex. That's a very comprehensive overview and a very nice introduction to our topic today. Thanks for taking time for this. And obviously, I'm sure you would get a lot of questions for the fundamental part and this material comparison. However, I would like to really direct our discussion towards the business opportunities and the development of your company and where actually our members here could help you with. Can you comment on this? What is it that our members of our community could do for you?
Well, so it's not enough to have a wafer, right? So no matter how good the material is, it cannot be accepted for the actual production until things like these are known, right? And so what we're looking for partnering with people who actually make devices, and that requires foundry component because unlike CMOS, where people are typically vertically integrated, so most semiconductor companies until very recently were making their own devices. Now, of course, it's going more and more to foundries, but in photonics, I think it was foundries from the start. And so uh, we need to work on acceptance of barium titanate by foundries because people who want to buy our wafers are asking where they can process them. That's not an easy question to answer. And then, if you remember the very first slide I pulled out from Richard Sorif's review, let me go back to it. And it's not my assessment, it's their assessment. So right here, you see that barium titanate, it's possible to integrate with CMOS. Yeah, it's fully compatible with CMOS. So nothing is volatile, nothing contaminates. And it has, in principle, in terms of like, power and area and all of that, it's good. But it's a new technology and not much is known. And so what we would like is to make friends with people who are willing to try, uh, make devices, because most devices you hear about are probably made by universities. So there are two companies that we're aware of. One is Lumiphase. They're working on a PIC. And then there is PsiQuantum, which is working on the quantum computing. They are not publishing much data on their devices. So we are looking for people to partner with in various forms so we can push barium titanate technology forward because it requires processing capabilities, it requires obviously device capabilities. And there are two ways of using the material. We think that the best one is to make everything in barium titanate proper. But of course, people already have working architecture, so you want to use barium titanate in the area on the chip where you want it. And for that, you can either do wafer to wafer bonding or die to wafer bonding. So we're looking for partners in that. And so we hope that we can find these partners in the EPIC ecosphere.
Okay. Clearly, yeah. And I'll be very keen on putting you in contact with Alex after this meeting. So please feel free to reach out to him directly or through me, and Epic will be happy to install those collaborations. So let me remind everyone that so we have a question and answer session after each talk. And if you have a question in mind, just push this raise hand button at the bottom of your screen and I pass you the word. So I see we already have one there from Matthias from SIA Systems, please.
Yes, hello.
Hello.
Alex, thank you for the nice overview of the new material. It's very exciting. In one of your last slides, you showed the position of barium titanate on a 300 millimeter wafer. And
Correct.
you mentioned there an excellent uniformity of 3%. My question is there an advantage if you would further decrease this value to lower than 3% for device yield or any other properties?
Well, certainly. I mean, silicon wafers proper have probably higher uniformity than this. So I think what happens essentially, if you look at this wafer, it's slightly different color at the edge and in the center. So there's some kind of a radial distribution. Also, you can see that the center is somewhat different from the edges. So of course it will benefit, but this must be good enough. My understanding is that I don't see personally, I do not see the number of PICs which require 300 millimeter wafers. But I believe it is the co-packaged optics, the TSMC, and they work on 300 millimeter wafers, which pushes people to that size. I think that if you start working on that with very few wafers, you will saturate. We are on the order of 10 million PICs, which are 10 millimeters square cross. So you can calculate how many wafers you would need. So I don't think there is a market for this size of wafers. But the technology, which 300 millimeter facility, silicon facility, like PsiQuantum works with global foundries. And so I think that's what drives this size.
Okay, thank you.
Yeah, thank you for your question, Matthias. I believe we have another one from Jorn. Epiphany, please.
Hi, thanks. So we're a design house, right? So we design for photonic chips. And my basic question actually is, so you showed that 72 gigahertz or so was achieved, I saw. The
Yes.
question would be, what is the limiting factor there? So if the curve factor is so much higher, why not? How far can you push it, and what's limiting it, right?
Well, so and this is my sort of anecdotal evidence. It is very expensive to go to high frequencies, right? So once you let's see, how does it go? If you want to go and stay below 40 gigahertz, the VNA system you need to buy is on the order of $150,000. If you go to, let's say, 200 gigahertz, you are already in several $100,000, and then it becomes more expensive than the ultra high vacuum deposition system. So there are very few people who can do material testing at this level. I think it will work to terahertz because you'll of course diminish the response because lattice cannot respond above probably 6 gigahertz. So you'll be at a half value at best. And then of course there is so in this paper they I think talked about absorption losses. This, however, I think that because IBM uses slightly different way of depositing. They use molecular beam epitaxy, so there is some absorptive centers there. We use RF sputtering, so I think that absorption is not an issue. They thought that Q 10 to the 6 is the limit. I don't think it's the limit. I think you can make a better material. But mainly I think for us, for example, we don't have access to high frequency measuring, so we have to find people who do.
Yes, if that is limiting you, then contact me. So in our supply chain, we have people that can measure up to 100 gigahertz, right?
Excellent.
So that shouldn't be the problem. The other thing is that we need, of course, in order to design proper electrodes for you, need the material properties very, very precisely, right? And that is often crucial in doing good designs and having good material data first. And lastly, there's Rapid Photonics, by the way, here in the Netherlands. I can put you in contact to them. They are working on BTO, integrated photonics. That could be interesting for you.
Excellent. Thank you so much.
Indeed, thank you so much, Jorn, and we'll be perfect to set up these collaborations you mentioned. All right, so if there is no further questions, I suggest we thank our keynote once again for a great introduction, and we now shift the gears and we'll talk about the other material that has been mentioned already, lithium niobate, and they will be represented by Hamid Satari, the founder and CEO of a new guy in the crowd, Seacraft. And Hamid will talk about the TFLN integration, monolithic ambition, and heterogeneous power. Welcome, Hamid, whenever you're ready.
Excellent. Thank you very much. Do you see my screen?
Sure.
Okay, very good. Thank you very much. It's a pleasure to be here. Thank you very much, Alexander, for very rich presentation, and this will help a lot to my presentation. In fact, I am Hamid Satari, co-founder and CEO of Seacraft, a new foundry that manufactures thin film lithium niobate chips. Briefly about Seacraft, we are a spin-out from Swiss Center for Electronics and Microtechnology. After 6 years of development in our in-house fab, we decided to spin out to industrialize this technology. And the key factor here to notice is that we operate from our in-house facility. This is quite important because we have full control over our recipes, and this is quite important for the IP, and also it brings flexibility in our recipes. We have been working with customers since 4 years in CSCM. We were offering the platform through pre-commercial offering, and this helped us a lot to know a customer's pain and to know that how we can add value to their products. So it is clear that one material cannot handle all the operation needed for photonics, but basically TFLN is chosen for ultra-fast modulation and maybe frequency conversion. And today focus is basically in datacom and telecommunication market. That's why high bandwidth operation of lithium niobate is really in focus. But there is no commercial foundry offering TFLN in volume and reliability required for industry. Briefly, if you just compare lithium niobate with mainstream PIC materials, you see that for modulation, TFLN seems to be the option to choose. And at Seacraft, we focus on further maturizing the technology and bringing access to broader ecosystem to adopt this technology. So if you look at the value chain for photonic integrated circuits, in fact, reliable manufacturing at high volume is the missing block that brings the bigger value to the chain. It's not like semiconductors that fabless companies and design houses, they bring the biggest value. TFLN stands in unique position because that's already recognized by industry, thanks to experience of industry working with bulk lithium niobate. And in fact, with TFLN players, we believe that this is the best material for photonics because its options goes beyond datacom and telecommunication. That is enabler for quantum, optical computation, advanced sensing, and so on. Yet the missing block is industrial grade manufacturing, and with Seacraft, we are closing this gap. When we are talking about thin film lithium niobate, Alex nicely covered that is quite unique material, hard to etch and pattern, and you need dedicated facility for that. This is one of the barriers that taking lithium niobate to a standard CMOS foundry. We did this. From day one, we have been working in an industrial environment. You don't need big fab because the market demand, you see that still TFLN is niche inside a niche market. And from day one, we developed a technology that today is the most advanced in the world. I'm talking about number of technology steps. We don't only etch one waveguide. We etch lithium niobate in different levels. We have several metallization layers. We protect this with clad, and nicely we open this cladding in different levels for integration and advanced circuitry and so on, all in industrial environment. And it's not only fabrication, that is also protected by de-risk PDK. So not only simulation, but also manufacturing and testing in more than 10 cycles has happened. So we provide customers also with the measurement data supporting all individual building blocks. So in terms of solution, so we provide different solutions based on our foundry processes. First, monolithic lithium niobate. We are running MPW 2 days. You can also jumping into dedicated custom runs for you and qualification for high volume runs, all empowered by tested PDK. But look, silicon photonics needs to get enhanced immediately. One option would be microtransfer printing. So you need a supplier for thin film lithium niobate chiplets to take those chiplets and put on your silicon photonics. We have developed a nice recipe with high yield. We deliver wafers with 10,000s of chiplets ready for your silicon platform. Today, ready. We are ready to engage with people. On top of that, we are really substrate agnostic. If you somehow bond your lithium niobate dyes or wafers on your silicon photonics, we are here to just continue from there. So process lithium niobate, back-end of line processing, metallization, and so on. We tested few of our recipes for TFLN on TFLT, and the result turned out to be amazing. So we see some traction on TFLT, and we do internal development to also offer TFLT in near future. And also from customer interaction, we see that they like to have monitoring photodiodes in the platform. This is something that in research level, we have practiced several times. Amazing result we obtained, and we are thinking to obtain it. We are thinking to integrate photodiodes also in our platform in upcoming years. I'm talking about the short future. Today, we offer MPWs, dedicated runs, few wafers that they serve the best for niche markets in quantum and sensing, but also for qualification runs. We already unlocked the capacity required for high volume production from our certified foundry at CSCM in Neuchâtel, and in different phases, we are expanding our fab in the region. We have secured the clean room area. Now we are populating it with industrial tools to deliver 20,000 of wafers per year in next 3 to 4 years. So with this slide, I was thinking about, what are the options for TFLN technology from monolithic to heterogeneous? What's their status, pros and cons? Please note that this is just personal perspective from Hamid Satari. There are several points that you might agree or disagree. That is food for thought and discussion. Option 1, monolithic TFLN. Status clear, very strong momentum because of clear reasons and AI revolution. Pros, there has been several years of research behind thin film lithium niobate. Several papers that Alex showed, nice bandwidths, low insertion loss, and so on, and compatibility with value chain. If you complete this foundry part of value chain, whatever that works for silicon photonics, it will also work for TFLN in terms of integration. Cons, lack of reliable manufacturing at volume. And there is a big question. What's the meaning of volume here? It needs a bit further thinking. We enter to heterogeneous or hybrid domain. So whatever word that you pick doesn't really matter. So option 1 is TFLN on silicon photonics using microtransfer printing. From my perspective, it sounds interesting, but it seems that industry still lacks a bit confidence to adopt it. Pros is that you are really flexible in terms of where to place these components, and it might also bring some cost advantages. In terms of cons, so there is lack of supplier in lithium niobate side. We hope that with CCRAF we close that gap. Footprint limits, device size of lithium niobate is one of the, I would say, issues that Alex already mentioned, and generally lack of experience in terms of transferring these chiplets, and also PDK. Who will be the PDK owner? Who will develop it? So that there is still uncertainties around this technology. TFLN on silicon photonic bonded, either die-to-wafer bonding or wafer-to-wafer bonding. To me, it seems that is the only viable solution for silicon photonic that could really save silicon photonic to continue its life by enhancing modulation. Compatibility with the standard tools and methods is there. Again, lack of foundries. So weak supply chain and wafer size mismatch here is important. So silicon photonic already moving to 300 millimeter, lithium niobate industrial supply for wafers that is still in 6-inch. And if you add lithium niobate on top of silicon photonics and other processing, so yield will drop. So it will take years to get to the yield that you get with monolithics, and lead time issue. So you add process and other steps to your full process, so chips will be delivered later than monolithic case. Final option, last option, TFLN as modulator. You bring photodiodes and lasers to TFLN. This is really the dream of TFLN, guys. Big thing, lithium niobate as the main platform for photonic integrated circuit. Today, that is in very low TRL. And personally, I don't see any solution provided by this approach in the next 5 years. Of course, the biggest advantage is that all-in-one based platform for many applications, not only for data and telecom, very wide range of application you can provide with this approach. Cons. What I see that is missing now is a vision. Why we do this? While maybe other approaches with heterogeneous integration could get better results faster, more yields, and lower cost. So no supply chain today. Final presentation, final slide. So what CCRAF can do for you? The most important thing is that today we have chips for you. You can order chips from us. You can loan chips from us to test start your product development, monolithic, heterogeneous, and foundry services. We are also very interested in co-development and joining the force to have partnership to strengthen the supply chain. What we need from people, of course, we work closely with PDK enhancement and enablement partners. OSAT partners, we want to work closely with them to move our measurement standards towards industrial grade. Quality assurance is quite important. And telecom datacom demonstration with big players, that is, of course, something that we can join force, small companies together to convince those big players that this is our technology and we have clear path to scale this up. With this, I would thank you and I am open for questions.
Nice, very nice presentation, Hamed. Great to hear about the developments at Seacraft and also the progress on TFLN. I'm sure this should raise some questions. Is there any in the audience? In the meantime, I will ask myself, do you think, Hamed, that there is a complete supply chain for TFLN inside Europe, or does Europe have to rely on external sources?
So with wafers, we are going to good direction. With design houses, we have very, very strong design houses, I would say, in Europe. In OSATs, I also see nice movements. And considering the niche nature of market, still, I believe that in Europe, we are above moderate, but still we need 3 to 5 years development as a whole ecosystem to strengthen it further. But of course, if you move further to our system side, that is really the biggest market that is in Europe, that is in US.
Okay. And what about this issue with the footprint of lithium niobate? Do you think it can become a roadblock?
No, I don't think it will be a roadblock. So for a while, if you compare with electronics, that I believe it's not right to compare with that. When you found the solution to have, let's say, 10 micrometer MMI bending below 1 micrometer, then we can talk about the modulator. So I don't think that Photonic is at the point to push for more and more components per chip. It's still, you see that NVIDIA even advertises bigger and bigger chip. It's how you relate the story. The bandwidth and insertion loss, these are the most important things to push. Chip size will be okay.
Yeah, indeed. I mean, the perspective is wonderful. So I wish you all the best with these developments, and I hope there will be an interesting follow-up coming from this meeting for you as well. So is there any further questions? If not, we thank Hamed again, and we switch to our next speaker, who represents Alluvia, and this is Carlos Asornio Martinez, the integration photonics engineer, who will talk about revolutionizing photonic integrated circuits with aluminum oxide technology. Welcome, Carlos.
Yes. Thank you, Ivan. Thanks for the introduction and thanks for the previous speakers also for the very nice presentations. And indeed, I'm very happy to present today with you how we can revolutionize photonic integrated circuits using the aluminum oxide technology of Alluvia Photonics. So I will start briefly giving a company overview. Alluvia Photonics was founded in mid-2022 as a spin-off of the University of Twente in the Netherlands. So we are basically a PIC manufacturer. We provide photonic integrated circuits based on the aluminum oxide platform to our customers. Right now, we are a very small team. We are five people in the team. And yeah, currently we are working with 4-inch wafers, which our fabrication we perform at the clean room facilities of the University of Twente, which is this picture that you see here, the Mesa Plus Nano Lab. However, for future, we're already exploring with the tier 1 CMOS foundries for developing our process in 8-inch wafers, so that we can deliver volume for the applications that need them. Then I would like to tell you why are we interested in the aluminum oxide PIC platform. Well, here in this graph, I show you the main three players that have been in the photonics environment in the last years, including indium phosphide, silicon photonics, silicon nitride, and then here at the bottom, let's say the most recent players that enter into the ecosystem, which is lithium niobate and aluminum oxide. So here we show the transparency window of all the material platforms, and we see that the other material platforms, we're missing a commercial photonic circuit platform that can deliver devices that work in the UV range. So here's where the aluminum oxide comes into play. Aluminum oxide has a very broad transparency window all the way from 200 nanometers to the mid infrared. We have demonstrated very low losses in waveguides. Let's say in the telecom wavelength, we are in the order of 1 to 5 dB per meter. And in towards the UV, let's say we have demonstrated around 1 dB per centimeter at 405 nanometers. Another important advantage of the aluminum oxide is that we can dope our material with rare earth ions, and that means that we will enable lasing and emission in different wavelengths. For instance, if we dope with erbium, we have demonstrated around 20 dB fiber to fiber net gain, and I will talk a little bit later about this. So what we offer as a company is we offer validated photonic integrated circuits in our platform. We are strongly collaborating with some design partners, Lucida, VLC Photonics, and Epiphany. And maybe Jörn can tell a little bit more about that in his presentation later. So we offer multi-project wafers. These multi-project wafers are meant for the on-doped runs, so basically just the passive aluminum oxide. And we offer two standard layer thickness, one 100 nanometer that it's meant for the UVs, and another one 400 nanometer thick for the near infrared. So we have these MPWs every 3 months. So if you're interested, feel free to contact us. However, we also have dedicated runs in which we can explore a little bit more, let's say non-conventional processing in case the application needs it. And we also have dedicated runs for the active devices. So this means erbium doped aluminum oxide, for example, mainly used for amplifiers, which I will talk later in the presentations. And we also offer right now a demonstration kit of our erbium doped waveguide amplifiers. In case that the customer needs packaging, we're also collaborating with PICs for that, which is also here in the Netherlands. So that's a very nice ecosystem. We have Epiphany, we have us, and then we have the packaging also, all within one block. So as I was mentioning before, aluminum oxide has very low loss propagation from the UV to the mid infrared. And here we just show a nice image of a spiral propagating light in the 369 nanometer. And we show the loss as a function of wavelength. And we see here the very low loss in the 1550. And it starts going up as we go down in wavelength. And right now our losses are dominated by the sidewall roughness, or we're working to reduce this roughness and further decrease these losses. Another advantage of our material platform is that it is it is very linear and very it handles a lot of power. So we have observed for wave mixing only when we have around 50 watts continuous wave inside the ring. The nonlinear index is comparable to silicon dioxide. So this means that it's basically very linear material with high power handling, which is for telecom applications is suitable to ensure the signal integrity. As I was mentioning before, we can dope our material with rare earth ions. It is very soluble, so that means that you can put a lot of ions, and then basically it will dissolve well into the matrix. In this slide, I present a demonstrator that we had also in collaboration with PICs, an erbium doped waveguide amplifier. This is a 50 centimeter long spiral. And with this device, we demonstrated almost 25 dB fiber to fiber gain in the small signal, with an output power at the fiber of above 50 milliwatts. So that's quite nice. And noise figure around around 6 dB in the 1550. So this is very specs comparable to the erbium doped fiber amplifier. But the advantage that we have here is that we have a reduced size and reduced cost as well. We have had also other demonstrations using different rare earth ions, in this case, thulium doped aluminum oxide amplifiers, in which we have demonstrated 1 watt of output power when we have a 36 milliwatt input signal. Also, amplification of pulses up to 800 watt peak power, and also low noise figure. And yeah, important to say that we're currently working for developing amplifiers in the O band, which are very important now for the AI and data centers. So basically, this slide summarizes a little bit of the EDWA technology. So basically, with Alluvia's platform, we can deliver the performance of the erbium doped fiber amplifiers, but with the size and scaling of semiconductor optical amplifiers. So yeah, that's kind of combining best of two worlds, and yeah, that's what we offer as Alluvia for the amplifiers. And with that, I would like to thank you for your attention, and I will be happy to take any questions that you might have.
Thank you very much, Carlos. Interesting presentation, very exciting developments you do at Alluvia. And I welcome everyone to raise your hands if you have questions for Carlos. Yeah. In the meantime, maybe you can underline again what is that missing for Alluvia to develop further? Maybe do you lack some partnerships in terms of material production or device testing? Can you expand on this?
Yeah, so I think we would like to have some measurements at the wafer level in order to check the yield of our devices at the wafer level. So some wafer level testing would be nice, which we currently do not have available. And also, of course, some demonstrators. Right now we have shown, for instance, for the erbium doped waveguide amplifiers, we have had a few demonstrators, but always nice to do some joint collaboration and have some other demonstrators. So if you have a nice application in mind in which you might benefit of our compact amplifiers, we will be happy to talk and see if we can do something together.
Okay, perfect. We will make sure this happens. And if there's no further questions, I'd like to thank Carlos again. And we'll move to our next speaker, who is Giovanni Zaffarana, industrial chemist at SAIS. And Giovanni will talk about the strategies for reducing contaminants in sealed optoelectronic devices. Is that right?
Yes.
We'll switch gears a little bit and we talk about the supporting materials on the field of integrated photonics.
Okay, can you see the screen?
I believe it's coming. Okay, you're all set.
Okay, thank you. Thank you, Ivan, for the presentation. This is Giovanni Zaffarana from SAIS Getters. And I would like to thank you, Ivan, and the EPIC teams. And I would like to introduce our strategies for reducing gaseous contaminants in the sealed optoelectronic devices. SAIS Getters is a material advanced company focused on the R&D, and so we provide many products that are based on functional metals and functional chemicals in order to upgrade and solve some problems or troubleshoot inside the devices. Sorry. Our areas, our market areas cover different technologies like the optoelectronics and photonic devices and sensors, and we provide you products like the functional coatings or barriers or many other dispensable getters in order to trap gases contaminants like water, like hydrogen, and many other molecules that can reduce the performance of the devices. For that, if we focus the attention on the optoelectronic hermetic packaging, in particular with the laser diodes or laser modules or transmitters, optical fibers, many other devices, sometimes contaminants like moisture, first of all, or hydrogen or other organic compounds may degrade or reduce the performance of the devices in terms of oxidation, corrosion, many other chemical reaction that can provoke the signal attenuation or shifting or cracking if we consider that inside the devices there are polymeric resin or other components. And for all, in particular, we point the attention to the level that is acceptable of the water that is set in 5,000 ppm for water and 1,000 ppm for hydrogen. So it's important to clean up the inside of the device of the packaging, reducing the amount of water and the hydrogen and other compounds. So the question is, what derive this kind of contaminants? In particular, moisture can be desorbed from porous or polymeric materials, or can be react with hydrogen or with other oxide layers inside. And hydrogen can desorb from metals or for plating, from plating, sorry. And the organic molecule compounds can desorb from the glues, from the epoxies, and for other polymeric compounds. So SAS-Getter's solution are here reported. In particular, we have 3 products: Z-Dry hydrogen that absorb hydrogen and moisture, Z-Dry-M that absorb very high level of moisture, and Z-Dry VOC that absorb both VOC and moisture. In particular, Z-Dry hydrogen can absorb up to 13% of nominal moisture capacity and up to 40 cubic centimeter per gram of nominal hydrogen, and also the hydrogen and moisture absorption are not competitive. Z-Dry VOC can absorb 8% of moisture and 5% of VOC, and Z-Dry-M can absorb up to 15% of water. In our laboratory, we perform some tests in order to understanding which is the adsorption performance, in particular changing the temperature of the devices. And we still provide that up to increasing the temperature from room temperature to 120 Celsius, the adsorption still remained at 50% of the effectiveness absorption. So the question is, what is the remaining water inside the package? And for that, we are performing the isotherm of water in order to understanding, increasing the temperature, what is the humidity still remaining inside the packages. Another features of our products is the reducing of the reflectivity. For that, we perform some tests with a laser, setting the input power at 20 milliwatt with a solid angle incidence or 45 degree, and we measure the reflectivity with the blank sample versus our Z-Dry-M black version. And so you can see that the reflectivity dropped down from 50% to 0.15%. So this is another results that highlight that we can reduce the scatter light and the destroy light inside the device system and the packages. Another features in this case with our Z-Drive VOC product is the difference of absorption depending of the nature, chemical, or the organic compounds that you can that are inside the devices can be desorbing from polymeric materials. And in particular, we perform some tests with ethylene, for example, ethanol, or methylethyl ketone, and we measure how is the uptake of these different organic compounds with the Z-Drive VOC, and this depends from the chemistry or the chemical-physical point of view, or the affinity of the compounds with our polymeric resin that are made our products. And also another issue of our products is the environment of activation. So if you use the standard activation, in particular using vacuum to -5 of millibar and 120 Celsius, we can ensure that the absorption of organic compounds can reach the maximum uptake if we compare the other activation, for example, in the air condition or nitrogen condition. So standard curing with a high vacuum can ensure a good quality of absorption. We also perform in our laboratory a system that is a specific analytical system from ONEDA Research Service, and this service can operate at temperature 100 Celsius and with other specific features like the quadrupole. And with this system, we operate with the dummy devices in order to understand which is the amount of water remaining in the package that has the Z-Dry-M. So with an optimized process, the amount of water it's up to 1,000, 2,000 ppm. But if we improve the degassing process and we activate our product, the amount of water remaining inside the packages drop down below 5 ppm and other. So it's important not only to use our getter inside the package, but it's important to activate properly in order to reduce the quantity of moisture inside the devices. So for that, the hermetic package can suffer for the gases inside the devices, and our film integration Z-Drive family products can improve and can drop down the amount of gases contaminants. So tailored getter materials can be integrated in order to improve this kind of performances, and not only the absorption is important, but also the temperature of the devices, the radiation absorption, the reflectivity, and also the organic compounds. So what we can offer for you is our customized getter films, the advanced management and solution for moisture and other gases inside, and the continuous optimization and improving the performance of our products and also for your business. And what you can do for us is share the device requirements and troubleshooting and many other problems, to collaborate and co-design testing in order to defining the priorities and the performance of your package, and provide feedback in order to improve our technology and the know-how. Thank you.
Nice. Very nice presentation, Giovanni, and it's very clear the use of these getter materials that you offer. And yeah, indeed, I believe it's a very important topic for all kinds of optoelectronic materials, but can be also used in the integrated photonics we mostly discussed today. So if you have a question for Giovanni, please raise hand with that button at the bottom of your screen, and I pass you the word. I see there is already a question from Jorn. Please go ahead.
Thanks. So I have a question. We have a few customers that work on gas sensing. So they certainly they want to measure certain gases, but not others. So what's your advantage? What would you say? How should they improve their package?
You say improve in terms of electronical point of view?
No, because we're sensing, right, in the same package. But there are also other gases around, right? So what would be your approach?
Okay, for this, all we can provide is to measure what is the water inside the package and also the residual gas analysis. So we can measure the overall the gas inside the packages, not only moisture but also nitrogen, helium, carbon monoxide, carbon dioxide, and make a plethora analysis of the overall gases inside the package in order to understanding which change the environment of the gases inside the packages. We also can make this kind of service.
Okay. Yeah, that's good to know that you have this service to analyze gas. Okay, thanks.
Yeah, you're welcome.
Yeah, you think, Giovanni, some kind of selective percolation of those getter materials can be possible for different gases?
Yeah, depending on the business of our company and from the company that ask this kind of service for us.
Okay. Yeah, and another question is, what is the best way to get a sample of your getter materials in case somebody wants to test it on their systems?
We send some products in order to test our materials. So we can also send the free samples in order to use our products, but we prefer to dispense our products on a lead that company sent to us in order to provide the lead that can be sealed inside the devices with our getters, because sometimes the different activations and curing, so the consolidation of the polymer can be some issue for the other companies. So we prefer to share this kind of information and also to provide the lead with the products inside, just to operate on the devices once will be sealed.
And for any of this, you would be the right point of contact, correct?
Yeah, of course. I can also share my information, contacts, and any other things that would help our people.
Okay. No, thanks, Giovanni. And so, yeah, please feel free to contact him or reach out to me so I could put in contact in case these getter materials might be of interest for your developments. So let's thank Giovanni again. And
thank you all, everyone.
We'll move to the next speaker, who is Matthias Nestler, the Director for Product and Technology at SIA Systems. Welcome, Matthias. And Matthias will talk about structuring and uniformity improvement of thin film lithium niobate and other waveguide materials.
Thank you for the nice introduction and for giving us the chance to introduce here our company and our products. We had already talked about wafer sizes like 200 millimeter that Alexander mentioned. Hamed mentioned the thin film lithium niobate material. Carlos mentioned the PIC device manufacturing, and I will introduce a technology for doing the material treatment, so the material processing and the manufacturing of PIC devices. So, and now I hope that, yeah. it switches now. So I think I can skip this slide since everyone here in the auditory knows what we are talking about, photonics integrated circuits. If I would go into details, it would be like carrying oils to Athens or sand to the beach. So I skip this. But allow me to give some first words on SCIA Systems. SCIA Systems is a specialist in film process equipment manufacturing. This equipment is typically based, in our cases, on ion beam processing technology and plasma processing technology. We have customers worldwide. We are existing since 12 years. We are based in Germany, in Chemnitz, and we had a revenue of about 100 million last year. Our main markets are in MEMS, especially in the RF filter manufacturing business for the mobile communication. We have markets in augmented reality and in high-end optics. Works like EUV lithography optics come into the game. And we look into this new topic of photonics integrated circuits as well. We have a global sales and service network, and we do a lot of technology and process development in-house. So we do not only sell equipment, we sell complete solutions to the customer. Yeah. What we are talking about, photonics integrated waveguides. The performance of such waveguides typically depend on some properties. We have some requirements. So we have special material, nonlinear optical material, lithium niobate or aluminum nitride, aluminum oxide. All these names already were mentioned. We need to optimize the light transmission in such waveguide material. We need to take care of the dimensions that have to fit to the wavelengths we want to transport over that waveguides. So that brings me to topics like lowest losses for total reflection, lowest absorption, low scattering, and of course, high yield on wafers. And so I have highlighted here two main parameters we are able to control. One is the thickness of such waveguides, and the other one is the structure fidelity. First, I want to switch to the ion beam trimming technology that addresses the thickness adjustment. And short introduction on the principle of ion beam trimming. So imagine you have a wafer, let's say a 200 millimeter wafer with a certain film on it, and the film has a thickness variation. The thickness variation can be pretty low. Here in the example, you have a variation from 368 to 360 nanometers, so just 8 nanometers variation. Sounds pretty smooth, but nevertheless, it may not be sufficient for your application. And therefore, we developed the technology that is called ion beam trimming. In the ion beam trimming, you see it in the schematics. You move a wafer in front of an ion beam source with a focus beam, a broad beam ion source with a focus beam, and you remove material on certain positions. It's a contactless high vacuum process with a very good depth resolution, close to single atom layers. The removal is controlled by local dwell time of the ion beam at a certain wafer position, and the dwell time adjustment is pre-calculated and then transferred into a velocity map for this raster scanning. We can also tilt our substrate to a certain angle to achieve there certain improvements. And finally, what you want to achieve is a very uniform film thickness distribution or property distribution of your devices, if you have already devices on that. Like shown here on the right picture, we improved here in this example the variation of 3 nanometer RMS down to 0.13 nanometer RMS by this ion beam trimming technology. This is one nice example. This can also be applied to waveguide. For instance, for lithium niobate waveguide trimming, here you do this trimming before you structure the waveguide, so just the bare film material is there trimmed to a certain uniformity. This can be applied for POI wafers, so lithium niobate or lithium tantalate and silicon, for silicon nitride films, for silicon oxide films, or silicon films on silicon oxide or SOI wafers. All these materials can be trimmed. Even other materials are trimmable with that principle. We achieve their uniformities of 0.1% and better. Here are some nice examples. Just need to switch it. Nice examples of lithium niobate trimming. So you see the pre-data in the left picture with some variation in the thickness, with a standard variation of 3.84 nanometer, and this could be trimmed down to 1.32 nanometer standard deviation with our ion beam trimming process. Also, silicon nitride is a material that can be trimmed. Here's an example of a silicon nitride film of 435 nanometers in average on a 2.5 micron silicon oxide film on a wafer. Here, even the pre and post data comparison. To make it more visible, I have put here also a histogram. So you see in the dark blue distribution, the variation of the thickness over a wide range of 425 to 450 nanometers, while after our ion beam trimming, all the measurement spots are close to the 400 nanometer target thickness. So here are the values. So we decreased the standard deviation from 4.8 nanometer down to 0.3 nanometer, really atomistic level, what we achieved. And I also like to mention here two other properties like the RMS roughness, where we did not see any negative effect. So the roughness pre and post processing stayed the same, 0.3 nanometer. And also the refractive index of that material, of the silicon nitride, stayed the same at a refractive index of 2.023. Post and pre is the same. So we achieved the improvement of the silicon nitride thickness standard deviation by a factor of 16. We did not change the roughness or the refractive index, means no increase in optical losses. And we have there also achieved the losses in the range of 0.14 dB per centimeter in some customer applications, but I cannot show any more detail on this. So here is a tool that is doing this process. It's a 200 millimeter tool, but can also be upgraded to a 300 millimeter tool with fully automatic processing of any film and wafer material. The film thickness correction could be down to 0.1 nanometer RNS. Typically, the processing takes a few minutes. Wafer size up to 300 millimeter. I mentioned already no edge exclusion since we have an electrostatic chuck that exposes the full wafer surface to the process. And with that, you can achieve a significant yield improvement, and throughput optimized design with two process chambers is also available for high throughput manufacturing demands. But we have also their R&D versions. We can also apply their technology, is called zero base edge function, to achieve also very, very low corrections with high precision. Then I switch over to our second property we will address with our ion beam technology, the structure fidelity. The structure fidelity, or the structuring itself, it's addressed by ion beam etching. Ion beam etching is similar to the trimming, but here we irradiate the full wafer at once with an ion beam source. The ion beam source is accelerating ions to the surface, and on the surface, the material is sputtered out, is removed, like it is shown here in this diagram on the right upper corner. And we can etch nearly any material as long as it has a sufficient high melting point and is vacuum suitable. Even multi-layer stacks can be easily etched, since the physical etch rate is more or less in the same order of magnitude for all materials. We call it ion beam milling or ion beam etching when we just apply noble gas in the ion beam source. So we hit the surface with noble gas ions like argon. But we can also apply reactive gas in such a process. Then we call it reactive ion beam etching. So we increase the etch rate and some selectivity. And further improvements can be achieved by a so-called chemically assisted ion beam etching. That is a mix of noble ion irradiation plus a chemical substance what is fed close to the substrate, to the surface. For patterning of, for instance, lithium niobate waveguides, we have some requirements like smooth sidewalls, and the sidewalls should be free of redeposition. And therefore, we have a two-step approach. In the first step, we etch perpendicular, means we etch from the top through our mask into the lithium niobate and create there the waveguide while we rotate the substrate, the wafer. And then for keeping the sidewalls clean, we tilt the wafer to a certain angle of, let's say, 70 degrees. And then we hit this side of the structure with an organ beam to clean it up. So, of course, in different times. So the first step is a long etching process, while the second one is just a short cleaning flash. And we apply there a mix of noble gas and reactive gas. So we apply there typically the reactive ion beam etching process flow with CHF3 as a reactive process gas. Here are some examples what can be achieved or what can happen also. We see here a waveguide that should be structured through a photoresist mask with a requirement of 75-degree sidewall angle, or larger than 75-degree sidewall angle, of course with low sidewall roughness and no redeposition. But the challenge here was that the photoresist was thermally unstable, and so the mask reflows and shrinks. What you can see here in this SEM photograph, that the mask doesn't look pretty well. And we developed their process combined by resist bake out plus a very improved cooling during the processing and a partially reactive process, and achieved there a nice etching of a lithium niobate structure. What you can see here in the SEM picture on the lower right side. Yeah, the tool where this happens is the Skiama 200. We have also here the 300 millimeter version available. You see here the picture of the version with 3 process modules and 2 load logs, so high volume manufacturing ready. We can process their wafers with photoresist masks or hard masks. We have good cooling. The etching angle could be adjusted with tiltable and rotatable substrate holder, as mentioned before, up to 300 millimeter. I also mentioned we optimized the system for high throughput with that robot system and multiple modules. And we have also versions as flexible tool for R&D and startup companies with just a single load log available. And this brings me to the summary. Here is a comparison of these 2 technologies once again. So on the left-hand side, the ion beam trimming for this thickness adjustment, and on the right-hand side, the reactive ion beam etching for structuring for this material. And with that, I'd like to thank you. And I'd also like to mention that we are at the Semicon Europe at booth B1470 available. If you like to meet us there, then you can visit us there. Otherwise, you can also drop us a message. And of course, you can ask questions now. Thank you.
Thank you, Matthias. Great presentation, and indeed a very powerful technique that seems to have a lot of potential in the materials we discussed today. I see there is a question from Alex already. Please go ahead, Alex.
Yes, Matthias, thank you very much. Excellent presentation. I have a question. Are you willing to try barium titanate? I think the process should be very similar to lithium niobate, but...
Sorry?
Are you willing to try 200 millimeter barium titanate wafer for the trim?
Of course, we are willing to try this.
Excellent.
So if you like to send us material, we have demo systems here available. We have 3 different trimming systems available for standard, for large substrates, 300 millimeter, and also for reactive trimming. So we can set up in DOE, and then we can run their tests and see the performance and what we can achieve. And that was also the reason for my questions for the 300 millimeter, if an improvement of the uniformity is an advantage. If you see there are certain chances, then of course we should try this.
Absolutely. We try to do this, right? Because barium titanate, the etching of waveguide is essentially ion milling. But we've noticed that once you make a waveguide, everything around it is also improved. So yeah. Milling is good. So would you be the point of contact if we reach out?
Yes, I would be the point of contact. Yeah, or yeah, you you can send it to the address given in the last slide of the presentation, but you can also direct it to me.
Excellent. Appreciate it. Thank you very much.
I will make sure to put you in contact. This is the spirit. Okay, thank you for your question, Alex. And is there any further questions? Maybe the lithium niobate guys. Have you tried this technique yet? Ahmed?
Since long time we have exchange with the SKIA, so this is just great technology, and also wafer suppliers should get involved there. There was a question that where this service should be provided, so we are really close to buying such a tool and having it in our foundry. But on the other side, we see that wafer suppliers, they say that, look, if you want service, we can already trim it and give the wafers trimmed to you. So this is
this is the philosophy. So we have customers that are device manufacturers and do the trimming. On the other hand, we have also customers in the field of wafer manufacturing, and so we are open. The best is to sell to both.
Absolutely, this is really problem solver. So we need this technology. I'm quite happy having this in value chain.
We have also, so we do not do trimming as a service, but we have also partner institutes that are happy to do this as a service. So if you are interested, we can bring you in contact with them.
Excellent.
Okay, thank you, Hamid, for your comment. And thank you, Matthias, again for the great presentation. So to follow up on the ion beam trimming technique, we have Daniel Pereira here. He's a sales manager for the semiconductor market at Buchler Group. And Daniel will continue on this topic and talk about advancing wafer uniformity for scalable PICs, POI, and SOI applications. Welcome, Daniel.
Hi, good afternoon. Can you hear me? Can you see my screen?
Yeah. We need your presentation
perfect.
now because we don't see the presentation, we see you instead.
You don't see the presentation? Okay. Okay. Now you see the presentation?
Yeah, now it's good.
Okay, perfect. Yeah. So thank you very much. Thank you as well for the introduction. Thank you to all the other speakers. So my name is Daniel Pereira. In a warm welcome from my side as well. I'm a technical sales manager for the semiconductor group at Buehler Leibold Optics. Today I come to present a little bit about our trimming technology as well, similar to what Matthias just presented in the previous talk. The focus here is on advancing wafer uniformity for scalable PIC, POI, and SOI applications. But before getting into it, I would like to first introduce you to our company. So Leibold Optics is a part of Buehler, and we bring to our customers a wide range of vacuum coating and trimming applications for a wide range of applications. So we're divided into different market segments, with each market segment having its own dedicated product portfolio for the different types of customers and different types of applications. But the concept is very similar throughout. We have a substrate. Substrate can be big, can be small, can be flexible, rigid, can be a wafer or anything else. And we do a functionalization of that substrate, which can be either via a coating tool, a vacuum coating tool, or can be via ion beam figuring or ion beam trimming solution. We are a Swiss company, so and within the Buehler Group, Leibold Optics has had a turnover of about 300 million Swiss francs last year. We are 600 employees scattered all around the world, with more than 3,000 systems installed. We also invest about 7% of our turnover back into innovation, and we are present all around the world. We have 3 application centers. One in Raleigh in the US, one in Beijing, China, and one in Alzenau, Germany, where I'm coming from. Our ion beam trimming tool is centralized in our center of competence in Leipzig. And there we have tools available for demonstration, for qualification of new products and qualification of new applications such as this one. So I'm here today representing our market segment, semiconductor, and the idea of this market segment is to merge the worlds of optics with the world of semiconductor. So meaning advancing optics and embedding high-end optics on a semiconductor level with semiconductor level processing, which means not only preparing the equipment, not only preparing the process for the optics, but also being able to connect our tools to the facilities and to the fab. So we prepare everything from all the way from the processing itself, but also to the handling and to the connection to the facilities. We are within the semiconductor group. We have magnetron sputtering tools, evaporation tools, ion beam trimming tools, and also ALD tools. We are focusing on different types of applications, but today the idea will be to focus on our pillar called photonic integration, where PICs and the waveguides themselves are focused mainly talking about our IBT or ion beam trimming tool. So Matthias made a very nice explanation of how ion beam trimming tool works, and this is basically the very similar concept to what we have in our IBT. We have generally two tools, the IBT 200 and the IBT 800 for wafers up to 200 and 300 millimeter respectively. These tools are also dedicated for full fab integration with connection from Smith and Fuchs. And they have installed high advanced ion source, which can then do the planarizing and the structurizing of the wafers on a nanometer scale. But why is this important? So to understand where IBT is most significant in the manufacturing of PICs, here it is important to have a look at the entire process chain. So starting first with the idea generation, then comes the design and simulation, the actual fabrication of the waveguides and the PICs, the testing, packaging, and then we have a finalized product. If we start looking into dissecting the wafer fabrication step, it all starts with the material platform that we have of choice, and we've heard already about a few of them today. So TFLN is one of them. We also have POI, SOI. We have waveguides based on aluminum oxide, as Carlos explained. We have a lot of different platforms and a lot of different materials that are being used. The next steps comes from the lithography, the material deposition, such as cladding materials for the waveguides themselves to protect the waveguides, cleaning, passivation, planarization, and metallization. So, and this might go through multiple iterations until the actual device is fabricated. So where does ion beam trimming start to play a role? So we have here two main points which could be very important, and where ion beam trimming can play a significant advancement in the industry. First of all is to talk about uniformity. So improving the uniformity of the wafer itself. And the second is in terms of micro roughness. So to increase the smoothness of the walls on the waveguide level. And again, why is this important? Because if we consider a wafer map, as you see here on the left-hand side, where you have what we are calling a non-uniform waveguide layer. So a traditional material coming from a CMP process, which gives a TTV or a total thickness variation of about 30 nanometers. This is an example. If we were to process such a layer and we would build the waveguides out of it and the actual devices out of it, we would have a range of thickness variation and a range of thickness of waveguides with different thicknesses. So when we look at the yield on the wafer level, some wafers would be within spec, but some of them would be out of spec. And this is because the precision of the waveguides and the precision of the thickness is very important, and even more important for PICs themselves. So an ion beam trimming step can reduce this total thickness variation even further to allow that the entire wafer or the entire devices within the wafer are within spec. So basically the end result is that you have an improvement in the yield of the PIC performance of the PIC platform production. And this can be applied for different materials, such as silicon nitride, lithium niobate. We also heard a little bit about lithium tantalate. So all of these different materials can be used for post-processing of IBT. So it's not that IBT will replace and can replace CMP, it's that IBT is a good add-on to a CMP process. So basically, if CMP and IBT work together, one of them can work on the volume removal of the material, whereas the other can do the final planarization. And this is described here on the thickness deviation within one 300 millimeter wafer. And you can see that basically CMP then acts on the thickness trimming, whereas the IBT will act on the planarization. So the other aspect that I mentioned in my slide before is in terms of the scattering of light. And this comes from the appearance of micro roughness on a wafer level. Here on the left-hand side, you see an example of a pre-IBT material, which was not processed. So the micro roughness, basically, if we build a waveguide out of it, light will interact with these microstructures and will scatter the light. The end result is that the propagation of light will be reduced. So if we process this micro roughness and we reduce them to even further, we will make sure that the light stays with where the light is supposed to stay, meaning within the waveguide. And there we can see then again that there's an improvement of yield on production yield if we reduce the micro roughness from here, example 0.5 nanometer to 0.2 nanometer. And this is within the scale of what IBT can do. So then here in the next slide is just an example of a few materials that are being used in different PIC platforms. Silicon nitride, lithium tantalate, lithium niobate we've heard about today, but other materials such as silicon oxide and silicon itself. We have some processes shown here. The highlight being here that we can process multiple materials with different types of wafer sizes, different types of layers, different types of structures. And we also can highlight that we have different starting points and resulting endpoints. But it's not just about the type of end result you get, it's also how long it takes you to get to such results. So for example, you see here highlighted 300 millimeter wafers and a 15-minute process to reduce the thickness, the total thickness variation of silicon nitride from 20 nanometers to about 5, but also reducing the RMS. And all of these results can be improved further with the compromise of time. So this is basically just an example of how ion beam trimming can be beneficial for multiple platforms. So in conclusion, and now here to get to the typical EPIC question, we are looking for partners in the landscape of PICs to further test and to further qualify our ion beam trimming tool. We can offer test tools. We have them available in our facility in Leipzig, and we can also integrate measurement equipment for before and after ion beam processing, and we can also control the in situ etch rate monitoring. So meaning we have a full rounded system that can be developed for R&D and mass production alike to improve the yield of wafer manufacturing. And here we are looking to investigate how much further we can improve our uniformity and how fast, how to reduce further the micro roughness, and of course to improve the wafer yield. I focused entirely on our ion beam trimming tool, but it's also worth mentioning that we have sputtering tools that we're also working in the waveguide field. In particular, we have a magnetron sputtering tool capable of depositing silicon nitride layers without any hydrogen in the process, which has proven to be very beneficial for infrared waveguides, which could be also very, very interesting in the field of 1550 nanometer PICs. We also have developed this with semiconductor in mind, meaning low deposition temperature processes. And we're looking to investigate topics like propagation loss. We already had some very, very interesting preliminary results, which I'm happy to share in the meeting. We also look into improving the fill factor and step coverage of our films and other topics. And just really to finalize, 2 weeks from now there's the PIC Summit in Eindhoven, and we are participating in the PIC Summit, but at the same time we'll also host our own event in Altenau. On November 6th, we will have a focus open house event looking into the scaling of photonic integrated circuits by vacuum coating and trimming solutions, basically focusing on these two tools. And we have a very nice lineup set up. So Lionix, IMEC, Mirax, and Synchron from different aspects. So from R&D side of view, from production point of view, and from different clusters of PICs in Europe. So if you would like to participate, feel free to contact me and I'm happy to host you. Thank you very much.
Thank you very much, Daniel. Great presentation. And indeed, it would be great to meet there at PIC Summit Europe upcoming soon. So yeah, this is, of course, we already discussed a very powerful technique of ion beam trimming. Is there any questions in the audience for Daniel and Buller Group? Okay, we have one from Giacomo Neolis, please.
Yes, I wanted to know about this trimming, ion beam trimming method. What about the stoichiometry on the surface? Because when you're using ions, usually you are just deplete oxygen. And for lithium niobate materials, for example, lithium is even more sensitive. So
yeah,
what about that?
We didn't study the stoichiometry after the ion beam trimming process, but we did some preliminary qualifications in devices, and we did not see a change. But this could be something actually very interesting to study.
Okay, thank you.
Indeed, a very valuable question. Thank you, Giacomo. Any other questions? Okay, if not, then I suggest to thank Daniel again, and we need to move on the agenda to our last speaker, Jorn Epping, the co-founder and CEO of the design software company Epiphany. So he will give us a very special look at the topic of today. Welcome, Jorn.
Yes, thanks, Ivan. But we are not a software company, by the way. We do photonic designs for our customers. No? Can you hear me okay?
Yeah, please.
Very good. Thank you. Okay. Yeah, so today I see that we have many different materials, and today I titled our contribution from design modules to lasers. So what we have now learned, yes, is that there are many different photonic integrated circuit technologies, right? So last year I talked to someone coming from the EDA software, so really from the electronics part. He said, I'm looking at the photonics landscape and it looks a little bit like Wild West to me, because you have many different platforms, and we've learned that they have really great advantages, right? For example, aluminum oxide bringing amplifiers on the menu card, or lithium niobate or BTO, really enabling high-speed modulators that are, for example, not reachable by silicon insulator easily. But in order to give people an overview, we indeed on our website made a mini PIC guide where you can look up the different material platforms and their typical application areas and some downsides and upsides. So if we look here, for example, in the spectral ranges, they really differ a lot. Going from down to 200 nanometers up to into the mid-infrared. But if we look at all these different material platforms, and I think all of them were mentioned during this meeting, that most of them need laser technologies integrated. I mean, Hamad said it for Seacraft and lithium niobate that's on their roadmap. But you see that except indium phosphide, all of them lack lasing materials. So this will be integrated at some point. So we see that we have a very fractalized supply chain. We have many different technologies. We also have many different packaging methods, but we also have many different EDA solutions, which, for example, small foundries with novel materials want to be reachable by many customers, and they don't want to stick to a specific EDA solution to do their designs. So that's where we also help. We help customers in the planning and design. We can also support fabrication and testing. So we have a broad supply chain. But also we do help people mentioning PDKs or helping people putting PDKs out there. And typically, if we talk about PDKs, there are many different ways to look at it. Many people see that it's sort of the Lego blocks that we put together, but that's only the upper level. It basically is an enabler for foundries to map their technology into software. And there we have profound EDA software expertise, which we help with a standardized way of writing this up. Then you can convert it and look out to and export it to different software for EDA solutions. For example, commercial vendors like Synopsys and Lucida is where we're working closely together for XPDK development, but also on the same hand on open source. For example, you want people to use the open source software that is available there if they don't want to, at this point, spend their money on other design software. And this basis on PDK is also for us the basis for EDA solutions. So what we have a design module philosophy. That means that both the PDK, we put an extra abstraction layers. So because the question arises, if we have so many different technologies, how actually do we transfer designs from one platform to another? So what we do on our side, we also enrich the PDKs on our side and remap the building blocks such that you can have very more complex building blocks that you can easily transfer between the different technologies. It could be as simple as an MZI or modulator, but it can. But we also are doing this with more complex functions. For example, filters or switches. Think about, for example, lattice filters, the way you really want to have specific filtering for wavelengths or other applications. Or what we're currently also commercialize or have other people evaluate is the hybrid lasers, where we have an external gain section, because we've seen that most of the technologies lack active lasing and will need some laser integration. So what we've done is we made a hybrid laser design module that can easily map on different technology. And we're currently in the phase of testing these out and really validating them. So we have it available for silicon photonics, on silicon nitride. Aluminum oxide is something that we are actually looking at also in a project together with Alluvia, but also lithium niobate is very, very, very interesting for let's say the next generation of coherent communication, for example. And on the other hand, we also have matching to our design module for your foundry, your technology that you choose. We'll also have laser chiplets already available, such that you can make one run at the foundry and just take off the stock, off the shelf gain sections that match with it to do validation. And on the other hand, what we'll also have available soon, currently in production, are evaluation modules. So you might be interested in the hybrid lasers we provide that you can put on your designs, but you want to test it. You want to test it. Does it work with my system? Is it reliable? Does it suit you? And then we can supply you already evaluation modules that you know that the design you put on your wafer run works for you. And with that, why can we do it? What we do? Because we are a service company mainly, but we have decades of experience going back with our CTO into the early 90s. which already did his first designs and commercialization of integrated photonics technologies before the .com. And with that, I would invite you to have a look at our website, have a look at our mini guide. If you have additions, let us know. Then we are happy to include more technologies or also talk with you about it. Other than that, I would like to thank you for your attention, and I'm happy to take any questions. Otherwise, I think it was a great meeting. Thank you.
Thank you very much, Jorn. Very nice point of view of the design house. Any questions for Jorn? In the meantime, I wonder myself, Jorn, do you see a growth of demand from people using a particular platform out of this lately? And also maybe some of the platforms that were not covered in the meeting today?
I think from our point of view, still silicon insulator has the highest traction at the moment. So that it was not covered in here, but it's the most mature, it's closest to semicon. And so I think that actually what Hamid said had very good points, right? Why not use the maturity of silicon insulator and add your secret sauce of lithium niobate on it? I think that's general valid approach. Same goes for indium phosphide. Indium phosphide can also be very well co-integrated with other technologies, for example, like XFAB is doing.
Would you be able to work with even more sophisticated platforms like polymers, graphene, maybe other things, plasmonic?
Yes, we as a design house are happy to work with that, right? As long as you find foundries that are open to share, and as I said, good material data on which we can iterate, right? And then we can work together and see, can also close this feedback loop, which is often needed, for design, fabrication, testing, and then you put it back into design and come to a better solution or more mature. I think that's important.
Okay, I see there is a question from Giacomo Neolith.
Yes, so how do you see platforms with multi-layers where you can have multifunctional stacks of layers to be combined, the various functionalities? This is the first question. And the second one...
Can you give an example?
Yes, for example, if you can integrate aluminum oxides doped with erbium between two lithium niobate to have active waveguides, for example, or if you can combine indium phosphides that can make good sensors with lithium niobate, or if you can combine this kind of silicon nitride on top of lithium niobate to have improved performances of the final device. This is the first question. And the second one is, what about additive growth to have directly patterned thin films with more performing architectures like we have seen for 3D printing in the mechanical field?
I think for your first question, I have to go back to the very first presentation of Alex, who showed that will depend on your target volume, what it's worth.
Yeah.
So how expensive can a chip be? That's the question you should ask yourself. And then it's how many process steps can you do, and if that economically feasible, rather than technical. And I think, yes, so we're working together with quite a few examples where people integrate different materials together, because, for example, lasers are missing in many of them, right? And I think lithium niobate on silicon insulator are a good approach to get silicon on insulator beyond the 60 gigahertz domain. It's a valuable approach. So I think the future has to go like that if we want to increase the speeds and data rates.
Okay.
All right, thank you, Giacomo. I think on the last point, Hamed can also comment. Go ahead.
Yes, thank you, Jorn. Nice presentation, and we had also good discussion in ECOC some days ago. I want to know your perspective about number of components per chip for photonic integrated circuits. Is there a push for some application to have it, or you work with different foundries, different material? I believe you should have better vision to this.
Mm-hmm. I think, from in my opinion, at the moment, it's not a lot, right? But so the typical examples I can name, what I already mentioned, is, for example, gas sensing, right? There you also have very easy design on a PIC that's feasible, gives better performance, right? And is quite scalable. Same goes for data center transceivers. They are also quite limited in their amount of devices. Another example would be, for example, in the more computing, optical computing, right? But there you are going to see how does it scale with yield, right? But I don't see a big push from that on our side. I have to say, most of the PICs are quite limited in their number of components, like not more than 20, 30. But
True, I was working in silicon photonics and trying to have 64 by 64 switch matrix. Okay, integration was good already. We could handle it inside the reticle size, but again, yield, even with silicon photonics.
yeah.
So the 1-2 component failing, then you reduce your matrix to 16 by 16 and so on, ending up by 2 by 2 switch working. Thank you for perspective.
But that also goes back to the question of the before, right? So if you're thinking about integrating something like 20 or 30 active devices in a hybrid manner, then you at least need a yield of 99% or so, because if you're at 89%, the total device yield will still be less than 50%. But I'm happy to see that microtransfer printing goes to that direction.
Let's see.
All right. Thank you very much for bringing up all these aspects. And thanks, Jorn, again, for this very nice summarizing talk and discussion. So we invite everyone to look at this web page that Jorn provided for comparing different materials. And of course, Epiphany is there to support you with the designs on any platform. All right, so this kind of brings us to the end of our meeting. Let me just share a few quick messages with you. So first of all, you now see there is a pool for giving feedback to us for this meeting, and I hope you all enjoyed it as much as I did. This was the online technology meeting on materials for photonic chips for you, and provided to you by EPIC, which is there to support you with technology expertise, market studies, opportunities in networking, mentorship, recruitment, and investment. I'd like to thank the team of EPIC who made this meeting become possible. And also remind me one more time that the next offline meeting of EPIC will take place on 17th of November in Munich. Our host will be a very important member of EPIC Atecube, who is also located in Munich. And that meeting takes place just the day before Semicon Europe. So you can hit both events in one travel. And we have a very exciting agenda where we'll try to bridge our community of integrated photonics with the traditional semiconductor people, and discussing the two sessions on integrated photonics and 3D integration in microelectronics, as well as integrated photonics and wafer metrology. We have a very nice agenda coming up soon, so please save the date and hopefully see you in Munich with us. And this brings us to the end of my
pool. 10 is the best or 1 is the best?
10 is the best. So 10, everyone, please. that brings us to the end of my talk, and I'd like to thank all of you for your attention, and see you on the next EPIC online meeting. Thank you, everyone.
Thank you very much. Bye.
Thank you. Bye.
Thank you. Bye to everyone.
Thanks. Bye-bye.
Thank you. Bye-bye.
Thank you, gentlemen. So